couple of weeks ago we talked about exponential functions. Let's just talk back through what an exponential function looks like. I have the function f of x equals 2 raised to the x power. So I'm going to pick the x values of 0, -1, -2, -3, 1, 2, and 3. If I do 2 to the 0 power, remember anything to the 0 power is equal to 1. If I do 2 to the first power, I get 2. If I get 2 raised to the second power, we get 4. And 2 raised to the third power is 8. We'll go back with the negatives. Remember 2 to the -1, that's the same thing as 1 over 2 to the first power. So when I plug in a -1, I get 1/2. 2 to the -2 is 1 over 2 raised to the +2 power, so that's 1/4. And 2 to the -3, that is really 1 over 2 raised to the +3 power, which is 1/8. So if you go plot those points, you're over 0 up 1, over 1 up 2, and you can see that my graph over 3 up 8, I'm drawing that exponential function that we talked about a couple of weeks ago. If x is -1, see I'm up 1/2, over 2, I'm up 1/4, over 3, I'm up 1/8. And remember, I will never get a y value of 0. So there's the exponential function. Now, according to what this up here says, remember this is the relationship between exponentials and logarithms. Y equals b to the x is equivalent to log base b of y equaling x. Okay? Now, remember, they're inverse functions. Those x and y's have changed places. So, here we have, that's supposed to say f of x. So, f of x equals log base 2 of x. Now, if these are inverses of each other, remember they're supposed to reflect, and you see it right here. It shows, here's the exponential function. This is what that logarithmic function is going to look like. And you can tell that they do reflect each other across that line, y equals x there. So let's talk through. We know that these ordered pairs should flip-flop. So I'm going to swap my y values. I'm going to swap my x's and y's, but I'm going to write down my x values over here. So I'm going to use 1/2, 1/8, 1/4, 1/2, 1, 2, 4, and 8, and show you that we're going to get these x values. So taking this equation right here, log base 2 of 1/8. Remember that says 2 to the what is going to give me 1/8, and we know that's a -3. Log base 2 of 1/4. Well, that's a fraction there. So 2 to the what's going to give me that 1/4 fraction. You know that exponent has to be negative. So there's that -2. Log base 2 of 1/2 is -1. Log base 2 of 1, remember 2 to the what will give you that 1. Log base 2 of 1 is 0. Log base 2 of 2, well, what is log base 2 of 2? It's 1. Log base 2 of 4, 2 to the what gives me 4, which is 2. Log base 2 of 8 is 3, because 2 to the third power is 8. Now, if I were to go plot these points, I'm going to start with 1, 0. So if I go over 1, I'm up 0. Over 2, up 1. Over, notice I don't have a 3 in here. Well, log base 2 of 3, 2 to what would get me a 3? There's not anything that we talked about. There is something, but there's some work that you have to do to figure it out. It's not real pretty, so we're not going to worry about that. We're dealing with things that we know we can get to that answer. So 2 to the second was 4, so I'm over 4, 2, 3, 4, up 2, over 8, up 3. Now, for the exponential, remember those y values never approached 0, never got to 0. They approached 0 but never got there. Well, let's go talk about these negatives. Look what's going to happen. If I go over 1/2, I'm down 1, -1. I'm over 1/4, I'm down 2. Over an 8, I'm down 3. If you notice, this graph just keeps going down. It'll go down forever, but it will never get to x equals 0. Okay, it will never get to x equals 0. So on an exponential function, the y value will never equal 0. So there's a horizontal asymptote at y equals 0 on an exponential function. And on a logarithmic function, there's going to be a vertical asymptote at x equals 0 because those x values can never get to 0. 2 to the what would get you 0, and there's not anything. So that's why. And you will never get negatives. 2 to the what would get you that negative number. There's never going to be a negative x value. So, if you notice, looking at the graphs, looking at the t-charts, those x and y values swapped places. The x became the y's became the x's. An exponential function is the inverse of a logarithmic function. So look at them. Here's a picture of the exponential and the logarithmic on the same graph. They do reflect each other across that line, y equals x. Now, something to keep in mind always on an exponential function, that you always have that ordered pair 0, 1. Okay, so you always have that ordered pair 0, 1 on an exponential function. That's your y-intercept, 0, 1. So 0, 1 is your y-intercept. Now, there's also another point that you can always tell. Remember that equation is f of x equals a times b raised to the x power? When x is 1, I'm going to plug a 1 in. So the base raised to that first power is base. Base times that a value. So anytime, you can always go and look and know the ordered pair 1 comma ab. Okay, you can always know that ordered pair. 0, 1 and 1 comma ab. You can always know those ordered pairs on an exponential function. Now, with that in mind, you always know 2 points on your logarithmic function. You always know the x-intercept is going to be over 1 up 0. That's always going to be your x-intercept, 1, 0. It's going to be the x-intercept every time. And then there's one more point. Over, see right here you have this point over 1 up AB. Look right here. This 0, 1 is the y-intercept. Well, on a logarithmic function, your logarithmic function is going to go through that ordered pair 1, 0. It's also going to go through the point AB comma 1. AB comma 1. Well, where does the AB come from? F of x equals a times log base b of x. Okay, this is equivalent to this. This is exponential form. This is logarithmic form. Remember, these are inverses of each other. So those ordered pairs have flip-flopped. So you always know those ordered pairs. So I'm going to stop this video here. It's almost 10 minutes long, so I'm going to stop and then I'm going to do another one talking about the domain, the range, the asymptote, the y-intercept, and the end behavior of each one of these.